yesterday and I couldn't go.
Wow. I wanted to go to that too.
I know.
How's yours?
Sorry for forgetting to mention the center mass. Okay. There wasn't much to say, right? I mean, that's not all there was to say. It's a useful frame to use because the moment is zero. It's useful. Okay, number one. The momentum is 2.65 kilograms C. Sorry, I don't have that. And the energy is 13.27 kilograms C squared. Okay. Number two, the momentum is 2.65 kilograms C. The energy is 17.27 kilograms C squared. 1 and 2 had better have an answer for the energy, right? Don't forget that something at rest still has energy. The momentum is the same as 1, 2.65 kilograms C, and the energy is 17.27 kilograms C squared. People are, of course, writing down, like holding on to answers for the future, right? People have asked me about like posting answers. It's actually not nearly as easy as you might hope it would be for me to do. So it's much easier for me, honestly, if you guys just write things down. In principle, you've done it already. All right, number 3 is 0.154 C. And number 4 is 17.06 kilograms.
What do you think?
All right, number 5, the energy is, I guess I have energy first, whatever. Number 5, the energy is 17.06 kilograms C squared, and the momentum is 0. Number 6, the energy is just about 13 kilograms C squared, and the momentum is 0.62 kilograms C. Number 7, the answer is 1.25 kilograms C squared, and the momentum is 0.75 kilograms C. Okay, that one I can do too, exactly. Energy is 1.25 kilograms C squared, 5/4, and momentum is 0.75 kilograms C, 3/4.
I hate energy.
Number 8 is 15.8 kilograms C squared for the energy, and a momentum of negative 0.75 kilograms C.
What was that?
The momentum?
The energy.
The energy? The energy is 15.8 kilograms C squared. For number 8.
Yes. And the momentum?
The momentum is negative 0.75 kilograms C. Okay. Number 9 is 1.38 kilograms C squared for the energy. The momentum is 0.95 kilograms C. Number 10, the energy is 15.89 kilograms C squared, and the momentum is 1.7 kilograms C. And the challenge is, in exact form, 5 root 1729 all over 211 C, which approximates to 0.985 C. Okay, a lot of stuff there. Pretty long assignment, really. What can I go over? What questions do we have? Yeah? 7 and 8, sure. Okay. The key to 7 and 8, which is also part of the key to 5 and 6, is understanding what the center mass frame looks like, right? The frame that we have, which I guess is sort of the default like Earth frame, I guess, we have, what kind of balls are these again? Beach ball and a crystal ball? Wait, no, that's later. I mean, initially, the volleyball and the saltwater taffy. Yeah. Okay. Rather has saltwater taffy, it tastes much better than it sounds. It sounds like it'd be disgusting. It's not salty, it's sweet. It's very sweet and it's quite tasty. It uses salt water somewhere in the making. I never made it, so I don't actually know. But it's not salty. You see some places like advertising fresh saltwater taffy, you should go ahead and have some. It's sweet and chewy and not salty. So there's volleyball heading and the taffy, saltwater taffy. And then they collide and they form a super ball, right? So that becomes, that's an arrow, not a happy face. So a single superball moving with some new velocity, which we calculated, right? Okay. The center of mass reference frame, which we always call CM. The center of mass reference frame, what does this look like? What does this part look like in center of mass reference frame? The total momentum is 0. What does it look like? Good. Well, equal with equal what? Good. Because they have different masses, they want to be equal velocity, right? They'll equal momentum. Good. So the center of mass frame, it looks like this. That they collide and they turn into what? Superball doing what? Not moving, right? Because the total momentum of 0 and the superball is the only thing in the frame, right? Then the superball must be stationary. Okay? So this is what it looks like in the center of mass frame. Now, then the superball explodes, decays into a beach ball and a crystal ball. The crystal ball, relative to the super ball, which also means in the center of mass frame, right, moves in this direction, right? Given that, if the crystal ball moves in this direction, which way does the beach ball have to move? It has to move the other direction so that momentum is conserved. Okay, in the Earth's reference frame, they move it, it's not clear which way they're moving, right? You have to actually do some calculation to figure that out. So I don't want to draw. The same thing happens, but they're boosted, right, by the fact that the ball is moving, so they'll have different velocities. But the center of mass frame is the one that 7 and 8 is asking about. So 7 and 8 asks about the center of mass frame, asking what are the energy and momentum of these things. Okay, well, we're given some information about the crystal ball relative to the super ball. But relative to the super ball also means in what frame? The center of mass frame, because the center of mass frame is the super ball's rest frame, or reference, right? They're the same thing. The super ball is at rest in the center of mass frame. It's the only object at that point in time. Okay, so the crystal ball has a mass of 1 kilogram and travels at 0.6 c. So this is a mass of 1 kilogram, a velocity of 0.6 c. Therefore, its momentum will be mu over root 1 minus u squared over c squared. And so that's going to be 3/5 c kilograms over square root of 1 minus 9 over 25. So that gives you 3/5 divided by 5 over 4. I mean times 5 over 4. Skipping a few steps, obviously, but doesn't cancel. And you get 3 over 4 kilograms c as your momentum. Okay, remember, if you started from use the calculator right here, you should go back and do it right so that you're ready for working with fractions. Okay. Otherwise, the test will not be good for you. Okay, and then the energy. See, if you know the mass and velocity, you can find the momentum and the energy. They both rely on the same variables, right? So the energy is mc squared over the square root of 1 minus u squared over c squared. And so that's going to be 1 kilogram c squared over the square root of 1 minus 9 over 25, and that is going to be 5 over 4 kilograms c squared. Okay, good. So we got the energy, we got the momentum. But in this reference frame, what do we know about the total momentum? It's not just conserved, it's also 0, right? The center mass, this is the center mass reference frame. The total momentum is 0. So if this thing has a momentum of 3/4 kilograms c, this must have a momentum of negative 3/4 kilograms c. So we can immediately write the momentum of this one. But hang on, we also know something else. We also know, so we know the super ball had a momentum of 0. We also know it had what its energy was. We figure that at number 5. Its energy is easy. It's equal to its rest energy, right? So just mass times c squared. mass we did is number 4. What was the mass again? Sorry. 17.06. Great. So here it's got to be 17.06 kilograms c squared because it's energy. Right? So how do I find the energy of the beach ball? Okay. The total energy is 17.06. The crystal ball has 5/4 kilograms c squared, right? Therefore, the energy of the beach ball is the total energy, 17.06, minus the part that the crystal ball takes, 5/4 kilograms c squared. At this point, you probably would be into the calculator mode, and that's okay. Right? At a certain point, the numbers get too bad, and that's fine. But at least for the calculations of energy and momentum, and really as far as you can go, you really should be using your fractions, especially those of you who reach for your calculator very readily, right? Like you should work on using your brain first before the calculator. Just like in other classes, use your brain to think about things before you look up the answer on Google. Okay, so that's how you, that's 7 and 8. Right? 7 is straightforward. 8 just takes a little thought about how the center mass frame, what the center mass frame is. Sir? Number 6, yes. Yes. So number 6 is based off the same thing, okay? Number 6 asks, so number 5, remember, asks for the energy and momentum of the superball in the center mass reference frame. Once you realize that at this point the superball is the only thing in the center mass reference frame, then it's very easy to figure out, right? Momentum is 0 and energy is just mc squared. But then it asks, what's the velocity of the volleyball in the center mass reference frame? That's a lot more complicated, right? And so to figure out that one, what we can do is this. I think the easiest way to do it, there's actually more than one way to do it, but I think the easiest way to do it is to do a velocity transformation. If we know the velocity of the volleyball in this reference frame, finding its energy and momentum is easy, right? So we want to find the velocity by just doing a velocity transformation. But wait a minute, to do a velocity transformation, use of x over here is the velocity of the volleyball, which is what? The nearest reference frame, which is 0.2 c. Okay, so you got that. The question is, v would have to equal the velocity of what? Of the center of mass reference frame. Right? Because I want to know the answer to the center of mass reference frame. So v is the velocity of the center of mass reference frame relative to the Earth. You're like, okay, what's the velocity of the center of mass reference frame? Right. Well, the good news is that the center of mass reference frame is the same as the superball's reference frame, which means the center of mass reference frame's velocity is the same as the superball's velocity. You see that? The reference frame's velocity is the same as the superball's velocity because they're the same thing, right? And did we find the velocity of the superball? We did. What is it? 0.154 c. Okay, good. So the velocity is in the positive direction. So the velocity is 0.154 c. Okay, so from here, now, you just need to find this one as us prime, right? You just use your regular equation. You work it all out, and you get that, and you're like, okay, great. And then once you have your u prime, then of course, you just say, you just plug that into, if you like that, right? Plug it into the equation directly, and you find momentum and energy too, right? Once you know the velocity, then it's fine. Go ahead. Yes. Sort of fine. And I mean, once you have this reference frame, you should be using only the reference frames. So you should be all use those prime.
When I was doing this, number 2, I couldn't figure out the energy of the super ball.
Of the super ball. Okay. Number 2 is actually the easy one.
I know.
And I mean, I'm not using that as a slight.
Yeah. You're not calling me stupid.
Yes, that's right. At this time. No, this is a very reasonable point. But and the reason it's reasonable is because that there's so many other things going on that it's easy to miss the parts that are actually easy. So we found an energy for this one, which was
13.26 kilograms times c squared. 26.
Okay, thanks. C squared. So we calculated that as just a formula, right? Now, this one, energy never gets to go to 0. Remember that? When it goes to 0, it
doesn't exist.
Doesn't exist. That's right. It goes to 0, it doesn't exist. So, in this case, we have the saltwater taffy. It's not an energy of 0. Its energy is equal to what?
Mass c squared.
Mass times c squared, right? So its mass is 4 kilograms.
4 kilograms.
Okay, so its energy is 4 kilograms c squared. Okay, the energy of the super ball is just the total energy. Energy is conserved.
Makes sense.
See, this is the one part where you can do it easily. That's why we do everything in energy and momentum. Those you can add. You can't add velocities, you know that doesn't work. You can't add masses, that doesn't work anymore. But you can add energy and momentum, as long as they're all in the same reference.
And then how do you find 3? Because I could have spent all this time looking for 2 and 3 and I couldn't figure them out.
What a great question. Let me give you a shortcut. You'll want these. I'll give you 2 shortcuts. And you should probably write these down as equations, like they're not their own equations, they're derived, but they're handy. Okay. So I see what you're saying now. So we have this, and we have this. Right? Now, what do you notice about the energy momentum expressions? They're really similar, right? They're both fairly complicated, and unfortunately, the problem is you need to solve for mass and velocity simultaneously. That sucks because there's square roots everywhere, right? And that makes it sucky. So in order to deal with this, what you need is a good, quick way to eliminate the square roots. Fortunately, there is such a way based on the fact that they are so similar to each other. Because they're so similar to each other, we can do something real nice. What can we do?
Multiply them.
Not multiply them, it's not the best thing. Divide them is going to be even better. So if we divide P divided by E, okay? And that means we have mu over the square root of 1 minus v squared over c squared over nc squared over the square root of 1 minus v squared over c squared. It all cancels. Virtually everything cancels. And you get u over c squared.
That's nice.
Okay.
So P over E equals u over c squared is one worth writing down and using. Okay, because it's really useful when you want to do number 3. For those of you who just shoved it into Wolfram Alpha, understandable perhaps, but no, there are ways to do it. You can use your brain. Okay. By the way, this thing here is often not, you don't find this around, you'll find it somewhere, but you don't find it around a lot, because they expect the physicists to be able to look at this and be like, oh yeah, you just divide them, right? And so that knowledge, that ability to do this is something that you want to develop, right? That ability to see through things. Computers can't do it all for you. I mean, maybe that 9-year-old or maybe they will, but then they'll take it over and you'll just have to obey the video overlord anyway, named Siri. But at least they'll speak to you in a nice woman's voice and like glow blue, and then one thing you can ask. All right, so that's one. Now, that one gives you velocity. Of course, once you know velocity, you can substitute in and get the mass, right? That might strike you as a little bit messy, right? It'd be nice to have an expression for mass too. All right, let's try this one. Let's calculate E squared, those are the square roots, minus P squared C squared. You're like, why? Let me show you. All right, what's E squared going to give you?
M squared c to the 4th.
C to the 4th. And the bottom of the square root just disappears, right? Okay, minus P squared C squared. What am I going to get?
M squared, U squared, C squared.
That's the C squared over same denominator. Right? Okay, good. There's some factoring that can happen here. The denominators are the same, right? So that's nice. There's some factoring that can take place here. So what can we, from this top part, what can I factor out? I can say m squared c squared, right? So m squared c squared will leave behind c squared minus q squared.
Wait a minute.
All right, well look, I don't like nested fractions, do you? No one likes nested fractions. How do we get rid of this nested fraction?
If you multiply the 1 to be c squared over c squared,
Good. Let's multiply by c squared over c squared.
you get square root of m.
We'll get
plus
x
square root of
squared c to the fourth times c squared minus u squared. And on the bottom, this will become c squared minus, and the c squared will cancel, c squared minus u squared. And now what happens?
C squared.
These can cancel. Be careful, when they get plus or minus signs, you can't cancel that easily, right? But when they form factors like this, then you can cancel them. And so we are left with something that is very, very, very important. Very, very, very important that you must take note of, okay? It's this equation. This is not just any equation. It's not just a shortcut. It's really, really important. B squared minus b squared c squared equals n squared c to the fourth. So important, I'm going to draw a box around it in another color to show its importance. I'll even draw stars.
That must be pretty important.
Is this more important than p over e equals u squared over c squared? U over
Yeah,
c squared?
okay, so this is really, really important. This is a fundamental importance, a fundamental statement of how relativity works. In fact, it is possible to start with this and derive all relativity from here. That's not how it happened, but you could. It's an extremely, extremely important statement in relativity. Oddly, it doesn't have a name. You would think something this important would have a name. However, it does not.
George.
So it's called the important formula? Or
Actually, it's called, the only person I've seen give a name is David Horan, who wrote the book that I've ordered and it should be coming in at some point. What's that book coming in? He wrote a book on relativity that I like and I think we'll use. And he refers to it as the very important relation. Because it's a very important relation.
We should call it Dr.
So he calls it VIR for short.
It's the most
It's
important.
very
Since he's the center of the
important
Let's call it George.
relation.
It's the
There really should be another name for it. But like, I've never heard one that people agree on. You should call it like Einstein's equation or something like that. But like, no one ever does. It's just, yeah, you know what it's like? Do you know why? It's like, you know how rate times time equals distance doesn't have a name, except for rate times time equals distance? Why doesn't it have a name? Because no, it's just so fundamental, right? That's just how, it's just the foundation of everything, right? It's almost the definition. And it's basically the definition of velocity, right? Okay, this has the same category. This is your rate times time equals distance for energy and momentum in relativity. Okay, it is extraordinarily important. Unlike this, this applies to everything, including light. Okay? Don't believe me? Watch. What's the mass of light?
Zero.
Zero. If mass is zero, then tell me, what does E equal?
E squared, C squared.
No, E squared equals P squared C squared. So E equals
PC.
PC. Do you remember that? I told you this before for light, and I said, I'll prove it to you later. Hey!
I thought we already did that.
So n equals 0, you get this? That's the equation for light. Right? Because mass is always 0 for light. What happens if momentum equals 0? Momentum equals 0, that means what's happening?
E equals MC.
It means you're not moving. And then what do we get? E equals mc squared, which is the rest energy. Right? It's like all there. Okay? This is a relationship between energy, momentum, and mass that is extremely, extremely important. Very, very fundamental to the workings of the universe. And the part that makes it fundamental is that minus sign. Everything in relativity, all the hard stuff in relativity can be traced to the minus sign. It's what makes everything weird.
So you're saying if that was a plus sign, everything would be easy?
Your plus sign actually things would be much weirder in a lot of different ways. The universe would be unrecognizable and so forth. But anyway, it's not. It's a minus sign. All right. Oh, is there anything else? Sorry. Anything else I can help on the homework? Yeah.
So for all these problems in different reference frames, they see like the paths of object. Is that the same thing?
They do, and I will get there. Maybe today, maybe Thursday. But yeah, we've been quietly assuming that, and that's because it's true. And so we will get there. Yes, sir.
So basically, everything except for mass changes in reference frames, but mass is the only thing that's not
It's
conserved.
not literally true. We will actually soon. I will soon be able to answer your question about what's conserved anyway. What is not conserved, but what is not relative, right? I can answer that question soon. Okay, we'll get it then. And I can actually give you a general answer.
So your weight is not.
Can't use math, but math is the only thing that
Well, you'll see what I mean. But first of all, we need to simplify things. Have you ever noticed that our equations are more complicated than they need to be? Have you ever noticed that?
always.
Have you noticed that things keep canceling out? That like they always cancel out. Some of you, in fact, may have already adapted shortcuts for dealing with that, right? What is it that keeps canceling out? B squared. C squared and stuff keep canceling out, right? Okay. On that note, the other thing that we might notice is SI units suck for relativity. Because they were designed by humans who work at human scales, right? So a meter is supposed to be the distance from the equator to the North Pole divided by 10,000. Did you know that? Or 100,000, or whatever what number was. Anyway, it's not perfectly accurate, but that was the original idea for a meter. The kilogram, don't know the story. But now it's the mass of this thing held in a very special location in France, right? And the second is, just some time.
It's like
It's a 60th of a minute.
It's
right?
the amount of time it takes a cesium atom to
Now it's
rotate.
to vibrate some absurd, silly number of times, right? Yeah. Which is a good definition for useful now. Where does it come from? It's a day, which actually is a physical unit of time, right? It's basically Earth, but it's divided by 24 divided by 60 divided by 60. That's a second.
Is the rotation the rotation
Okay,
is
6,400 seconds in a day. Okay, good. So those are dumb units used for relativity, right? Because all the numbers become extremely large or extremely small. The times are always really small, or the distances are always really big, right? The same thing happens with energies and momentum. If you actually worked in that that factor of c or c squared, you would get absurdly large numbers, right? So everything's really, really large. Velocities are absurdly large. So the units we're using are dumb. That's really what it comes down to. Why would you use those units anyway? They are not they're not natural units, as they call them. They are arbitrary units that don't fit well with relativistic work. So let's kill a few birds with one stone. We're going to choose our own units. They call them sometimes natural units, or sometimes particle physics units. Sometimes they call them that. All right? Here are our units. We are going to really unit is a question of what is one, right? What does one mean? 1 kilogram, 1 second, right? Okay, good. This is our unit. From now on, C equals 1.
That should make things
Well,
a
that
lot
makes
more
life
You're like,
easy.
wait, what? Can you do that? Well, C is a constant, right? In every reference frame, right? And for every time, C is always the same.
So E
So
squared.
you can set C to 3 times 10 to the 8th, or you can set C to 1, which if you think about it is a lot more sensible,
Yeah.
right? And what does that do to everything? Make it a lot nicer. A lot nicer.
So
Right? Some of you may have been doing shortcuts with this already in your work, which is fine.
You could have told us this earlier.
Yeah, I want to do something.
What if you have like relations with C squared and C?
No big deal. They both one.
Well, like
You're like, wait a minute. Doesn't that? Okay, watch what happens. So, for example, you that doesn't get rid of all our units. We still have other units. So, energy, for example, in particle physics, the standard unit of energy, and I'm a particle physicist, so I have a bias towards that. That's correct. Capital G, lowercase e, capital V. So okay, that's the unit of energy. Okay. Now, momentum. Momentum, if you notice, the unit of energy, momentum is compared to energy, is a factor of c, right? So, given this, what's the unit of momentum you can use? GeV divided by c.
Or is it 1?
Well, we'll do this for the moment, and then we'll set c to 1.
So momentum equals energy?
No, they just have the same units.
Mass equals energy.
Mass, of course, you can get the units right off of Einstein's relation. What would be the units of mass?
C squared over G.
Then try again.
GeV over C
GeV over c squared. There we go. Okay.
It's the same.
Micah, it's okay.
And velocity is, of course, just the c. Right?
I'm starting to see a pattern.
That they're all the same. So if c equals 1, what happens? Energy, momentum, and mass are all in the same units.
Yes.
Is that cool with you? No, that's cool with
Yeah.
me. All right, good.
I have no further.
That's
So,
pretty fine, man.
Oh, shit.
So that is why, if you ever look at something written by a particle physicist, you will see them say things like, for example, you heard a few years ago, a few more years ago now, when you were like, were you alive? 2012. No, you were still alive. Okay.
Not on the inside.
2012 was a big discovery at CERN. You guys hear about it? Yeah. Higgs boson. Yeah, there we go. The Higgs boson discovery at CERN, very big deal, very genuinely big deal. A lot of stuff that comes out in the newspapers is not actually a big deal. This one's a genuinely big deal. Biggest discovery of the century in physics.
September 8th.
Well, century hasn't gone on for that long, but biggest discovery since 1998 in physics. Okay. Sorry, energy.
Oh,
So, and in particle physics, biggest discovery since 1984. So, very good deal. What was, they discovered the Higgs boson, and what was its mass? 125 GeV. And if you ever go to look, plus or minus a little bit, they got it pretty narrow. And if you ever manage to look at it, then like you're like, wait a minute, that's an energy unit. And this is like, oh, yeah, I mean, over c squared, over c squared. Basically what happens is we speak of masses in GeV for like the whole time, and then when you're writing the paper, you're like, oh, I mean over c squared. And you probably, I bet you can find published papers that leave that out. Because they
well, we have to have that in for.
Oh yeah, of course.
We have.
Yeah, probably.
But we have to remember to have the C and over the C and the C squared for our
because of
presentation.
that reason, I will tend to go easy on you on this. Okay. It is possible I might take off some fractional points on the exam or something, but yeah. GeV is just an actually useful unit. When you're dealing with particle physics, that's the actual number, so that you don't use scientific notation to express your stuff. So that's the EV itself is an arbitrary unit too. GeV is a billion of this. Turns out to be useful for particle physics. Yeah. E. Yeah. So for light, now you get E equals V. When it's a momentum, what do you get? E equals M. Right?
Wait.
And the very important relationship that I talked about is really better expressed as E squared minus P squared equals M squared. And that's really what people use. E squared minus P squared equals M squared.
I actually think I've heard that before.
You might have heard that before. And if you take pause for a moment and think about it, it makes no sense. But then if you know the units, then everything's cool. Basically, it just means we are just going to remove all the C's from all our equations and everything will still be fine.
Energy equals mass times momentum.
Right?
Plus momentum.
If you notice, if you go back and look at everything you've done beforehand, it worked. Yeah. You can always remove all the C's and it was fine. That's why, as long as I did things like light seconds, right? Because I knew that extra factor of C and it always works to take it out. So we just got ourselves a set of much nicer equations, like gamma equals 1 over root 1 minus v squared, and p equals mu over root 1 minus u squared, and e equals m over root 1 minus u squared.
Oh.
What is the square root of 1 minus u squared anything?
No, it's just that's just and then that's not a unit, that's just math, right? And then, of course, now we can say that u equals p over e. And isn't that pretty obvious now that u equals p over e? And of course, you have e squared minus p squared equals m squared. The most important one.
Is for e there? Is that u squared?
Well, that's a u squared, yeah.
That just changes the.
I don't need you criticizing my handwriting, boy. I have a PhD. I don't need to be able to write. Yes, sir.
So then this also applies to the Lorentz transformation.
Yeah, Lorentz transformations become a lot nicer. A lot nicer.
Wait, does that say?
Oh my god. Oh my god. This is just. Let me take the difficulty path here.
Oh, hang on. There is one thing. First of all, if you need an answer that's in seconds, or meters, or some other predefined unit of time or velocity, you can't use this.
Dang it.
Well, you can, but you have to put them back. You have to put the c's back at the end and actually work them out, because velocity is distance over time. So if you need an answer in a set distance or time, then you can't use this. Now, if you work with light seconds, it still works. Turns out. Okay, but if you need something in meters or seconds at the end of the day, then that means you have to plug in a numerical value for c, right? Which means you need that c back in. You're converting to SI units, right? So you have to watch out for that. If you need an answer in meters or seconds, or if you're not using light seconds, I guess I should say, then that means you'll have to actually plug in a numerical value for c, right? But that almost never happens. I mean, I just say leave all your answers in terms of c, and you do. And if the c's weren't there, you wouldn't notice, right?
Yeah.
And so we're going to do that. So here's what you do. You do the equation, you do all the math without c's, and then in the end you say, what kind of answer is my result? Is it an energy? Okay, then I'll tack on an energy unit. Is it a mass? Okay, then I'll tack on that extra over c squared. Is it a velocity? I'll stick on a c. Okay? Because c equals 1, you can put on as many factors of it as you want. It equals 1. So you just make the units work at the end. Yep.
What is the particle physics units for distance?
I think we typically do distance in 1 over seconds.
Over second?
C
1 over seconds,
per
right?
x.
Distance equals velocity over time, so velocity's in c, so 1 over seconds. We typically do time in seconds and distance in 1 over seconds. We don't use them very much. No. Oh, no, it's 1 over seconds, right? It's light seconds is c times seconds, right? Yeah, it still works out. So anyway, yeah, then particle physicists, we call particle physicists use this, particle physicists use them all the time. We never use c. We use them. And like I said, we forget about them, and then like, oh shoot, this is being published. So, and then we put it in. All right. Yeah, he does that a lot earlier than I do. I like watching you guys suffer. Yep.
Could you give us an example of how this would work, like within an actual equation or something?
Sure. You know how we had that problem that we're working on, like this one here? Okay. So P equals mu over the square root of 1 minus u squared. The mass is 1 kilogram. U is 0.6 or 3/5 over root 1 minus 3/5 squared. And the result of that is 3/4 kilograms.
Nicer.
GV.
And then you're like, oh, this is supposed to be a momentum? Oh, it's a momentum. All right. And then you tack on.
Oh! That's amazing.
Well, this one I didn't give it to you in GeV, right? I gave it to you in kilograms, so you did it in kilograms. This is, the kilograms thing is sort of transitional. You don't usually do stuff in kilograms, but you can. It's just a vector C, right? No big deal. But more often you'll be given
My
energy,
mind was
momentum, or
blown.
mass in terms of usually GeV. People, there are other MEV, people use other units. You could use joules, you could use other energy units, but GeV is most common these days.
So that if it was given.
Right.
No.
Okay. All right.
Corruption.
So,
This makes me happy. How long
it
does
should
it
make you
last?
happy. It should make you happy. Okay, thus armed, thus making things quite a bit easier, we are now prepared to look at numbers 9 to 10. And how did you do numbers 9 to 10, provided you did that? You did a velocity transformation. You have to take these things here, from P and E, find the velocity, which we now know how to do easily, right?
Yeah.
Find the velocity from here, then do a velocity transformation back into here, and then use that velocity to find the energy momentum again. Quite a bit of work, huh? Don't you think there should be, shouldn't we be able to encapsulate that all into one equation? The answer is yes. Yes, we can. So let's go do that. Okay? Let's find a, let's find the transformation rule for energy. So what I really want to know is, if I have some reference frame, I have another reference frame moving at velocity v, same setup as always. There's something in here, but now it has a certain energy, right? It's moving, it has some energy, it doesn't have to be moving. There's some energy, this reference frame is an energy E prime, right? This is why I didn't want you to use gamma, because I'm going to have to use gamma now, right? I don't want you to use it beforehand. So, all right, so that's how we want to work it out, right? Okay, well this thing has an energy E, and it also has a momentum P. I'm going to stick that momentum P in because if I know the energy and momentum, what can I find real fast?
The velocity.
The velocity I can find real fast, right? The velocity in this frame is P over E. Remember how we showed that? Okay, good. So now I have to do a velocity transform on that, right? So U prime is P over E minus V over 1 minus P over E. Oh boy, this gets so much easier now that I have to do P with 1. P over E times V. That's C's, right? Isn't it nice without C's? Like, it's so much simpler to write things. Okay? I can simplify this equation by multiplying the top and bottom by E. Right? Multiply top and bottom by E, then I'll get P minus EV over E, that's a lowercase p, isn't it? E minus PV. Okay, it's kind of interesting, isn't it? All right, great. So I want to figure out what the energy is now, right? Okay, good. So the E prime, the new energy, would have to be m over the square root of 1 minus U prime squared. Oh, no more C's. U prime squared.
Oh.
Right? Okay. Wow, U prime squared. That doesn't look very fun. Well, here, well, that's fine. Okay, here we go. I'm going to do a lot of algebra. You don't need to do all this, really. Like, I'm going to derive the answer and use that. Right? So don't freak out about the algebra. But I'm good at algebra, so let's do it for you. I want you to see it, right? So you can see that I'm not making this up. But you don't have to write down everything or worry about doing it this yourself. Like, that's fine. Okay, so here we go. 1 minus this, so I just square this. Let's write out the top.
Wait.
E squared minus 2PEV. What did I make a mistake? Okay. Let me know if I do, because I did that.
Yeah.
And then the bottom I actually, well, the bottom I guess we'll go ahead and
Okay,
write
I'm
out.
not writing all those things.
E squared minus 2PEV plus E squared V squared. Okay, good. Well, let's do this common denominator and all that, right? Woo! All right, here we go. M over. You know, for this is do not be afraid of algebra. Like something like this, you see this, you don't be like, oh, there must be a better way. You're just hard to do it. It's not hard, right? It's just a little bit of math. I have seen much worse. Okay, so that's common denominator of E squared minus 2PEV plus E squared V squared. And so now I subtract this, so minus P squared plus 2PEV minus E squared V squared.
Look at
And
all
something remarkable happens. What happens? Okay, see it?
Yes.
Cross term cancels. This term here and this term here, identical terms, but different signs. They cancel out. Okay? Well, that's nice. Let's see what we have left now. All right, we have m over, and what do we have? I have e squared plus p squared v squared minus p squared minus e squared v squared. All over, I'm going to go ahead and recollapse this back down to e squared minus pv, e minus pv quantity squared. Okay, that expression in the numerator is not as hopeless as it looks, because it's actually e squared minus p squared, that's these two terms, minus, and if I factor out, a negative b squared from these two terms, it's minus b squared times e squared minus b squared.
Isn't e squared minus p squared equal to something?
See that? In fact, I just rearranged the terms and took the second two and I factored out a b squared from them. And aha, then of course you have a factor on the top of e squared minus p squared, which by the way, what is e squared minus p squared?
Mass.
M squared, isn't it? Remember that? So, that means we have m over the square root of m squared, and you can factor that out, so it's m squared times 1 minus v squared over e minus p v quantity squared. And this is working out nicely, because now if I take the square root, I'll get m over m over e minus pv, because that square roots just cancel out those. There is this part that's still left under the square root of 1 minus v squared. Let's divide this properly just to make sure we can do it. So you multiply by the reciprocal, right? So e minus pv over m times root 1 minus v squared. Now you can see m's cancel. And what's 1 over 1 minus v squared? What's 1 over the root 1 minus v squared? If you put in a c, you can put the c squared back in, that's actually the same as gamma. This is gamma, right? Where c equals 1. So what this is equal to is gamma times e minus p. Well, let's put the p first by convention.
That's wonderful.
So, do particle
That
physicists?
turned out to be simpler than it looked.
So, which particle physicist came up with this simplification of everything?
This?
Yeah.
This is Einstein. Which particle physicist? This is Einstein. Come on. It took me 5 minutes to do that.
No.
So, this one's not the hard one. This is just math.
I mean,
Okay.
he was created. No, come on.
Well, that's cool. Hey, while we're at it, let's do momentum, huh? It's actually pretty easy because we already did this transformation. So now we can also do momentum. Momentum prime is.
I thought we just solved for moment.
Huh?
We just solved for energy.
That was energy.
Never mind.
That was energy. Yeah, we started with energy. Yeah?
So with gamma, so that only works with the where c equals 1, or it still works like
No, that works for anything. It's just C equals 1, just a choice of units.
You could put C's in there. It would just be really uncomfortable for me.
If you put C's in there, it would be E over C squared. Yeah. No, sorry. Why is it so hard? No, these units work. Never mind. Yeah, these units work. Okay, let's do P real fast. P prime is actually fairly easy because P prime equals P prime equals U prime times E prime.
And can we just take the two things we've already derived?
So U prime is P minus EV over E minus PV times energy, which is, by the way, gamma times E minus PV. So gamma times P minus E, or let me put V first by convention, V minus VE.
Huh.
Neat. Okay, now that derivation was fun, but you don't actually need to worry about that. You should worry about the answer. You shouldn't worry about it. You should rejoice at the answer.
It's the one.
Because it comes out pretty simply, doesn't it? Not just simply. Let me rewrite it. Okay, technically, momentum is a what? A vector. And what have I been assuming about the direction of the momentum? It's been in the x direction, same direction as velocity, which is always positive x direction. So I've been assuming really that this is px, right? Technically, there should be a px on everything. So if you put this together,
This is beautiful.
now, I haven't actually worked out the other momentum components. I'm not going to do it for you, because it's actually not trivial. You actually have to do a little bit of work to show this. So you're probably not too surprised to learn that the momentum in the y direction does not change, nor does the momentum in the z direction. And does this look familiar at all?
This kind of looks
It should look
like
very, very familiar. In fact, remember, if c equals 1, what do the Lorentz transformations look like?
Well, looky there.
Right? When c equals 1, it exposes a little bit more the structure of these equations and shows they're not just similar, they're identical. Right? They're actually the same transformation. Well, that's interesting, huh?
what a strange coincidence.
What'd you say? Good.
Does that mean time and energy, like,
Have something to do with each other?
yeah.
Hold on.
I'm
If you
assuming
notice
that
that energy is a scalar, why is energy a scalar, not a vector? And why is momentum a vector? Right? And Einstein was not the first one to realize this. A man named Hamilton, among others, figured out that not the same Hamilton. He's saying that's a lot, and he got shot. He realized that the fact that energy is a scalar and time is a scalar is related to the fact that position is a vector and space is a vector, and they go together in a very, very deep way. Yeah.
Because energy is scalar and the product is V and P, would be a vector or
VPX, that's why I had to put PX there. Yeah, otherwise it goes wrong. Okay, so what do we get from this? Well, it might give us a better idea of what to call a 4 vector. Okay? We're going to say a 4 vector is not just any 4 numbers. Okay? A 4 vector is 4 numbers that transform to different reference frames following the form of the Lorentz transformations. So you can have the space-time 4 vector. That's the space-time 4 vector. And you'll also have
The energy momentum.
the energy momentum 4 vector, E, Px, Py, Pz. Is the energy.
we'll be learning about other 4 vectors.
What did you say?
We'll be learning about other 4 vectors.
No. They exist, of course, mathematically. You can construct them. They are not useful. These two are very useful. The energy momentum 4 vector is far more useful than the space-time 4 vector. You might think it would be the other way, but it's not. The energy momentum 4 vector is incredibly, incredibly useful. And it is the heart of everything we do in relativity and particle physics. Because, unlike space and time, energy and momentum are conserved. They do everything better. Okay, let's do this. I don't think. Oh, I may have a homework assignment for you. Yeah, no, I do have a homework assignment. That's good. Yeah, I have something for you to work on for homework.
Okay.
I think. Well, you know, I'll just let it go. I'm looking at a test probably next Tuesday, I'm thinking.